Okay, so now we'll move on to zero error. Okay, how do you actually sort of make corrections, take into account the zero errors present in the vernier scale. Okay, so what happens when there's no zero error? Okay, very importantly, you need to make sure that in order to determine whether there's a zero error, you need to first make sure that the jaws are fully closed. Okay, and they are like fully touching one another. Okay, so if there is no zero error, okay, you can see that the zero mark on the vernier scale is exactly in line with the zero mark on the main scale. Okay, so you look at this line over here. Okay, look at this line here. The zero mark on the vernier scale and the main scale is exactly in line. Okay, so this means that there's no zero error, right? What happens when there's a positive zero error? Okay, a positive zero error happens when as you can see, the zero mark on the vernier scale. Okay, so this is the zero mark on the vernier scale over here. Okay, is in front of the zero mark on the main scale. Okay, so it is in front of the zero mark on the main scale. Okay, this is the zero mark on the main scale. The zero mark on the vernier scale is in front of the zero mark of the main scale. So this is called a positive zero error. Okay, so the value of the zero error, okay, is the value on the vernier scale which is in line with the main scale. Okay, so as you can see, the value on the vernier scale which is in line with the main scale is this line over here. Okay, so this will actually be the value of the zero error. Alright, so in this case the value of zero will be 1, 2, 3. Okay, so the value, the reading, okay, on the vernier scale will be 0.03 because if you can remember, okay, the accuracy of the main scale is sort of each division represents 0.1 cm. Okay, and for the vernier scale is 0.01 cm. Okay, so over here the value of on the vernier scale is 0.03 cm. Therefore, the value of the zero error is 0.03 cm. Okay. So how do we actually put it into the formula? If you can remember from earlier, okay, the correct measurement is actually just the actual measurement minus the zero error. Okay, so it's the same formula. The correct measurement is just the actual measurement minus away the zero error. Because why you want to take away the zero error? So you minus the zero error. So here the value of zero error is 0.03. So you just minus away 0.03. Okay, so positive zero error is relatively straightforward. Okay, now negative zero error is the one whereby it's slightly more tricky. Okay, so you have to pay close attention. Okay, so here, how do we know it's a negative zero error, right? So as you can see here, is the opposite of positive zero error, whereby the zero mark on the vernier scale is, instead of being after, is now before the zero mark on the main scale. So you can see in positive, this zero mark on the vernier scale is in front, but if it's negative, the zero mark on the vernier scale is behind the zero mark on the main scale, right? So here, when this happens, we know that it's a negative zero error. Okay, so same thing. Okay, how do we determine the value of the zero error? We look at the value just like over here. Okay, we know that this is in line. Okay, this portion here, right? So here it will be same thing. This is the line that's in line. Okay, so the okay, this looks a little messy, so okay, so just like this line over here. Okay, so that's in line. Okay, so over here in this situation, this is the line that is in line. All right, so this line will actually tell us, give us a clue. It doesn't directly tell us the value of zero error in the case of a negative zero, but it gives us a clue. Okay, we have to do one extra step. Okay, which is that the zero error, the value is the value on the vernier scale in line of the main scale, which is this line, but you have to do an extra step, which is you minus away 0.10 cm. Okay, you have to minus away, very important, you have to minus away the 0.1 cm, okay, in order to get the value of the negative zero error. So over here, so basically the difference between the negative zero and the positive is this negative 0.1 cm over here. You have to do this negative 0.1 cm to get the value of the zero error. Okay, so in this case, the value of the zero error will be, okay, and in the positive zero error, you just read it straight away. It's 0.03. Here, this value here is 1234. It's actually 0.04. Okay, as in the previous case, but you do this extra step whereby you minus away 0.1 cm. Okay, this is very important. You take the reading here, which is 0.404 cm, but you minus away 0.1 cm. So the actual final value of the negative zero error is 0.06 cm. It's not 0.04 cm, but it's minus 0.06 cm. Okay, there's a negative sign in front because why? You need to do the minus away 0.10. So after you minus away, you get a negative 0.06 cm. That's why it's called a negative zero error. Okay. So now, what do you do with this value of negative 0.06? You put it into the same formula. Okay, so it's the same formula: correct measurement equals to actual measurement, okay, minus the zero error. Just that in this case, the zero error, previously it was just a positive value 0.03. Here you have a negative value 0.06. Negative 0.06. So you sub it in negative 0.06. So it actually becomes a positive. Negative become actual measurement plus 0.06. Okay, but it's the same. So instead of 0.03 positive zero error, you have negative 0.06 subbed in, which is a negative zero error. Okay, so I'll move on to the explaining the micrometer screw gauge. Okay, so this is once again how a micrometer screw gauge looks like in real life. Okay, it has something called an anvil, a spindle. So the object will be placed sort of like here. Okay, and you actually tighten the anvil on the spindle, and then you will get a reading on the you call this the sleeve and the thimble, right? So you actually turn this to actually tighten it. Okay, and the thimble will actually rotate as it tightens. Okay, and once it fully tightens, okay, on the sleeve there's a main scale. Okay, and on the thimble there is a micrometer scale. Okay, and just like in the case of the vernier caliper, in the case of the micrometer screw gauge, you have to take the reading on the main scale and add it with the reading on the micrometer scale. Okay, so the reading on the main scale is in mm. Okay, whereas the reading in the micrometer scale is in 0.01 mm. Okay, divisions. Right. So in the main scale, each marking on the main scale represents 0.5 mm. Okay, so each marking on the main scale represents 0.5 mm. Okay, and on the micrometer scale, which is a rotating scale, you can also call it a rotating scale because it actually rotates as it tightens. Okay, it is actually 0.01 mm. So each marking represents 0.01 mm. Alright, so let's just go on to how to read the micrometer screw gauge. Okay, so first of all, once again, you look at the reading on the main scale. Okay, how many divisions are there on the main scale, which is the number of vertical lines that are visible up to the edge of the rotating scale, right? So you basically, let us look at this example. How do we get the main scale reading? Okay, here the main scale reading is 4.5. Why? Because we look at how many markings are there up to the point where it touches the rotating scale. So as you can see, it's represented by this blue arrow over here. Okay, the reading on the main scale is this arrow, this marking here. Okay, and how do we find out what's the value of this marking? Each one represents 0.5. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so sorry, 1, this is 0, this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 9 times 0.5. Okay, so it will be 4.5 mm. Okay, so the main scale reading is actually 4.5 mm. Another example whereby if it's just 8 divisions, it will be 4.0 mm. So I'm just over here, I just gave you 2 examples. Okay, so here is 1, 2, 3, 4, 5, 6, 7, 8. So 8 times 0.5, you get 4.0 mm. Okay, so 2 examples for you to understand and see how the reading of the main scale is derived, right? So what about the rotating scale? Rotating scale, you just basically look at the marking that is in line with the horizontal reference line of the main scale. Okay, so you look at the horizontal reference line of the main scale, which is over here. This is the horizontal reference line. Okay, and then you look at the reading on the rotating scale that's in line with this line. Okay, in this case, it will be here as represented by a green arrow. Okay, and it will be 20, 21, 22, right? So there are 22 markings, but each marking represents, okay, as you can see, 0.01 mm. So 22 markings, okay, basically just means it's 0.22 mm. Okay, and over here it is the same, it's also 0.22 mm. Okay, 20, 21, 22. So in the above 2 cases, okay, the reading on the rotating scale is 0.22 mm. Okay, so how do we get the final reading? Same thing as the vernier calipers, we add the main scale and the rotating scale readings together. Okay, so in this case, it will be 4.5 plus 0.22. Okay, that will give me 4.72 mm. That's the first scenario. Second scenario is 4 plus 0.22. Okay, rotating scales are the same. Main scale is just a difference of 0.5. So in the second example, it will be 4 plus 0.22. That will give me 4.22 mm. Okay, so same thing, I just add the main scale reading with the rotating scale reading. Okay, so sometimes you may encounter a strange situation, okay, whereby you'll notice that how to put it, the 0 mark on the rotating scale, okay, whereby this is the 0 mark, okay, as represented by this red line here. This 0 mark on the rotating scale, okay, lines up exactly with the horizontal reference line of the main scale. So as you know, this is the horizontal reference line. So this horizontal reference line, okay, lines up exactly with the 0 mark on the rotating scale. Okay, so what this actually means is that this line here, okay, I'll just use a okay, you can see this line here. What it means is that actually this rotating thimble actually is in line with a marking on the main scale. Okay, so there actually is a marking over here. Okay, so I'll just draw it in black. Okay, so actually underneath, right on top of this rotating thimble, there's actually a marking on the main scale like that. Okay, hopefully you can see it. Okay, so what happens is that it actually constitutes one marking. Okay, one full round, one marking, right? So there are 2 ways that you can see it. You can actually, because this marking here is actually invisible, okay, as highlighted in yellow, this black yellow marking here, okay, it's actually invisible because it's right underneath this rotating scale. So what you can do is you can actually just count up till the point before. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so you have 13 of them. So 13 times 0.5, because each marking represents 0.5 mm. Okay, so 13 times 0.5 is actually 6.5. Okay, but because you know that this thing represents, when it's on 0, it means that this rotating scale has rotated one full round. Okay, and each one full round represents basically 50 mm. Okay, each marking is 0.01 mm, so there are 50 markings, so it's actually 0.01 times 50 is actually, if you rotate one full round, it's actually 0.50 mm. Okay, so what happens is that you can just take this reading over here. okay, which is 6.5 mm, you add 0.5 mm, okay, you will get 7.0 mm as the final reading. Okay, so it's 6.5 mm plus 0.5, so 6.5 is this highlighted yellow, plus 0.5, that's one full round of the scale, you get 7. Alternatively, you can just take this as 0, okay, instead of seeing it as one full round, you see it as 0, but you take into account this marking over here that's underneath this rotating scale, so it will be, if this is 13, this will be 14, okay, this is the 14 mark, so it's just 14 times 0.5, you get 7 mm, okay, and here it will just be 0, so it's the same answer, 7 mm. Okay, so there are just two ways that you can look at this. So how do we actually understand like the calculation of the zero error, okay, and to take into account getting the correct answer, okay, for a micrometer screw gauge. Okay, so the principle is actually the same as that of the vernier caliper. Okay, so in the case of vernier caliper, okay, the jaws must be fully closed. Okay, here will be the spindle and anvil must be fully tightened. They must be in full contact with each other. Okay, with no object in between, they must be fully tightened. Of course, it cannot be too tight because you will spoil the screw gauge, but they must be in full contact with each other. Okay, so once they are in full contact with each other, you can start to see whether there is a zero error, right? If there is no zero error, what happens is that the horizontal reference line on the main scale, okay, over here, horizontal reference line on the main scale, okay, lines up exactly with the, okay, 0 mark on the rotating scale. So this is the 0 mark on the rotating scale. If it lines up with the horizontal reference line of the main scale, okay, then it is a situation whereby there is no zero error. Okay, so it's a bit small. Okay, so this is the 0, okay, marking on the rotating scale is in line with the 0 horizontal reference line of the main scale. Okay, so no zero error. What happens when there's a positive zero error? Okay, this horizontal reference line over here, okay, is above, okay, the 0 marking on the rotating scale. Alright, so when the horizontal reference line on the main scale is above the 0 marking on the rotating scale, okay, you will have a situation whereby it is a positive zero error. Right, so let me just try to draw this again. Okay, never mind. It's a bit too small. Okay, so yeah. Okay, so the horizontal reference line over here is above the 0 marking on the rotating scale. Okay, so if it's above, you have a positive zero error. Okay, so how do you determine the value of the zero error, the positive zero error? Okay, so you just read the part on the rotating scale that's in line with this horizontal reference line. Okay, so as you can see, this line here, it is the second line that is in line with the horizontal reference line. Okay, so it's 0, 1, 2. So the value of the positive zero error will actually be just be 0.02 mm. Okay, and based on the formula, okay, it's the same formula. The correct measurement is the actual measurement minus away the zero error. So the zero error is 0.02. You just sub it in, so it's minus 0.02. Okay, correct measurement is actual measurement minus zero error, which is 0.02.